Hello guys, and welcome back to another lesson in Unit 3, where we are currently looking at hardware, looking at all of the components within a computer system, understanding the different roles and responsibilities that each component has when it comes to a functioning computer. So far we've looked at the architecture of the CPU, which is quite a complex topic, but once you understand how the CPU works, the rest of the unit will make a lot more sense. So this next lesson is all about the performance of the CPU, how it's measured, and what kind of things can affect its performance in terms of completing what we call the Fetch-Decode-Execute cycle discussed in the previous lesson. So our learning objectives today are quite small, and we're looking at the terms core, cache, and clock speed within the CPU and explain how the performance of the CPU is affected by these three things. So if you need to go back a lesson to understand the basics of the CPU and all of the components inside, by all means do so. But in this lesson, we are only looking at these three terms, which are what we call the three C's, which are here. So first of all, we've got the cache, we've got clock and speed, and then we've got a core. So these three images I like to show to my younger students, but even for GCSE, it still makes complete sense. These three C's are the three measures that we look at when it comes to the performance of a CPU and how fast it can process instructions, which affects our use of a computer in terms of reliability, efficiency, and just general performance of a device. So first and foremost, we'll look at the cache. And I briefly mentioned cache in the previous lesson, but here we'll talk in more detail. And cache is a really small amount of memory, which is technically a part of the CPU. So whenever you're looking at a CPU, it will come with a certain amount of cache. Now cache serves a similar function to RAM, only it's nowhere near as big. Okay, the reason for this is that because it's so much faster, we have to sacrifice the amount of things we can store in order to focus on speed and performance. The thing that cache holds in particular is instructions that are constantly being reused. Okay, so any data or instructions that the CPU is likely to reuse, it will keep it in the cache so that it's much closer and much faster to operate as opposed to going back and forwards to main memory. Remember, main memory is RAM, which is where all of our open programs and applications are stored. But any data that the application might be using, it might be a good idea just to keep it in the cache so that the CPU isn't constantly going back and forward this way. The longer way, it can simply grab it from the cache and go straight back to the CPU because the access speeds are so much quicker when it goes to the cache. An easy to understand example could be if you're playing a game and that game is currently open in RAM. If something is constantly open within the game, for example, your current score or your position in the game, the CPU knows that this information is going to be used constantly or regularly. It will just keep it in the cache, so it's much easier to access than, like I said, going back and forward to RAM. Now, when it comes to levels of cache, there are actually three levels. This pyramid here represents storage in general, and down the bottom you can see external storage such as hard drives or external storage. Now what the pyramid represents is that the further away we get from the CPU, which is at the top, the amount of storage we have access to is a lot bigger. Okay, you can see capacity along the bottom here. So these devices tend to have more available memory than the ones closer to the CPU. However, as you might imagine, that must come at a cost, and that cost is basically speed. The closer we start getting to the CPU, we then move towards RAM. So RAM is smaller than the hard drive, but is much faster in terms of data storage. So the closer we get to the CPU, the further we get up the pyramid, the speed will start to go up. Now this pyramid is perfect for this unit because it also applies to some of the other lessons which we'll come to in a later date. But like I keep saying, that the closer we get to the CPU, the faster data transfer is, however, the smaller amount of storage is available. Now as you can see, above RAM we have cache, and there are three levels to it. And what we need to remember is that cache is technically a part of the CPU. Now the first level, level 1 cache, is the fastest out of the three, but it's extremely small, typically between 2 and 256 kilobytes. Each core, which we'll get to in a minute, has its own level 1 cache. But more importantly, it's very small, but extremely fast. That's the most important thing. The closer we get, the faster it goes. However, the smaller storage is available. So level 1 is the closest to the CPU. It's the smallest, yet it's the fastest. Obviously level 2 moves a bit further away, so the amount of space goes up as we go from 256 kilobytes to 8 megabytes. However, it's not as fast as level 1 cache. Okay, so we're getting a little bit further away. It's still very fast, especially compared to RAM, but it's not as fast as level 1 cache. And then finally, level 3 cache is measured somewhere between 4 megabytes and 50 megabytes. And again, this is more, but as you imagine, the speed is decreasing as we go down the list. So level 3 is the slowest out of the 3, but it is still much faster than RAM. Okay, you need to remember that. So cache, all levels of cache is still faster than physical memory, in other words, RAM. So why cache affects performance is that if we can store more data closer to the CPU, this is going to make the CPU run a lot smoother and allow you to store more frequently used instructions, making the CPU just work generally faster. So something that you need to consider when you're buying a new CPU or buying a laptop and looking at the CPU specifications is how much cache it has available. But typically they are generally the same around modern processors, but it is something to consider, especially if you're a technical person and like looking at the specifications in a lot of detail. So coming away from cache and we're looking at clock speed, this is the second C. Just like a speedometer on a car, the clock speed indicates how fast your CPU can run. Now the way this is measured, just like a car is measured in kilometers per hour or miles per hour, is in what we call megahertz or gigahertz. Now this comes back to the Fetch-Decode-Execute cycle, which we discussed in the previous lesson. And the Fetch-Decode-Execute cycle is the process in which the CPU gets an instruction, decodes it and executes it. So it's basically how many instructions a second the CPU can process. So if you imagine a human, depending on what the instruction might be, this is going to vary. If our instruction is to pick up a pen, this might take 2 seconds. If our instruction is to wash the dishes, this might take 5 minutes. So our instructions are going to be a lot different because the CPU processes millions, if not billions instructions every second. So how this is measured is that one cycle of the Fetch-Decode-Execute cycle would mean 1 hertz. So if the CPU is doing 1 cycle per second, that would equal 1 hertz. However, it's doing a lot more than that. And that's where the term megahertz and gigahertz comes in. So megahertz means a million and gigahertz refers to a billion. So a typical CPU in 2025 has at least 2 gigahertz of clock speed, which means 2 billion instructions are fetched, decoded and executed every single second. So as we've mentioned, it indicates how fast the CPU can run, and this is the measurement in which it uses. Okay, so gigahertz is the modern measurement that's used, and we are typically in this range from anywhere 2, 4, even 6 gigahertz CPUs exist nowadays. But something we need to be aware of is that the faster the CPU runs, the more energy it requires, and the more heat that will be created. That's why keeping a CPU cool is so important. And finally, we have a core. And a core is a part of the CPU which contains an ALU, a control unit, and its own registers. So if we go back to the last lesson, we discovered that these 3 components are what makes a CPU. Now that's if we're talking about a CPU that has 1 core. However, it's very common for computers to have dual, quad, or even octo, which is 8, and even more as we move forward in time. Now what this means is that if we've got a dual core computer, that means a CPU has 2 ALUs, 2 control units, and 2 sets of registers. 4 or quad core would mean we'd have 4 ALUs, etc., etc. So if you can imagine, if a CPU has 8 ALUs, 8 control units, and 8 sets of registers, it's able to do things simultaneously, independent of each other. So each core is able to run independently, not interfering with the other, which means you can run multiple programs, more high-end applications, and just generally increase the performance of your device. So it's very important to remember what a core contains, as well as remembering how a core affects the performance. Obviously, the more cores you have, the better the performance will be, but you also need to recall what's inside of a core. A question I've seen quite a few times is to describe what components are inside a core, to which you would state an ALU, a control unit, and a set of registers. You wouldn't need to go into detail of the registers, but just describe that a core has its own registers. Then being able to say a dual core or a quad core is like having 2 CPUs or even 4 CPUs, and so on and so forth. So again, more cores means more power and better multitasking. So just to finish off, a nice simple question. Out of the 4 CPUs you can see listed, which is theoretically faster? We've got a dual core processor running at 2.7 gigahertz with 4 megabytes of cache memory. We've got a quad core running at 1.5 gigahertz with 8 megabytes of cache memory. a single core running at 3.2 gigahertz with 2 megabytes, and finally a dual core running at 3.2 gigahertz and 4 megabytes of cache memory. So some simple maths, we have to times this one by 2, this one by 4, this one is just 3.2, and then times this one by 2. So a dual core with 2.7 gigahertz is essentially like having 5.4 gigahertz. A quad core with 1.5 would be 1.5 times 4, which is 6 gigahertz. The third one's a single core, and the dual core at 3.2 will be 6.4. However, we've also got to look at the cache. So the first one only has 4 megabytes, the second one has 8 megabytes, third has 2 megabytes, and the last has 4. Now, although the fourth one has a higher overall number in terms of processing power, having 4 cores means the 4 cores can work independently, which is going to help a lot more when it comes to multitasking. Not only that, the second one also has more cache memory, which means it's able to store more frequently used instructions and again will help in performance. So the second one is theoretically the fastest because of this quad-core system that it has. So hopefully this makes sense, guys. The CPU is one of the trickiest topics within this unit, so hopefully from here it does get a lot easier. In the next lesson, we're going to look at the term instruction sets, and again, it's another tricky topic, but I will do my best to explain and make it as simple to understand as I can, and I will hopefully see you there. Okay, guys, see you next time.